Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about Triac, basically a AC silicon switch. So let's dive deep into it. So what exactly is the problem that we need Triac to save our day? Well, our world, like the whole world, and I mean every single sector that you can think of, generally day to day requires a switching system. And generally your switching is supposed to happen on a signal. Like whenever you switch a light or light bulb, you are directly mechanically doing a big work. Now, cool, awesome, GG. But what if you want it to be a feedback loop? Basically, what if let's say water temperature reaches to this point, then turn it on, or what if you reach this point, do this, those sort of things. So in those sort of scenario, you want some signal, thermal signal, physical signal, whatever have you, a signal to drive a big load. Now that's a hard task to solve, and again, majority of humanity is just dealing with that. It's basically how to have a tiny signal do a big ass work. So we have been doing that for millennia, so to say, and we have been using relay, contactors, bimetallic thermostats. Basically, we figured out that electromagnets are on-off magnet system. So what if you have a spring-based system and that spring stays in one state, but when you power on the electromagnet, then you change it physically move it from one place to another, and then you convert it into a switch that you can electrically control on and off. So this coil could consume, let's say, 10 watts of power maximum, and this can easily switch upwards of 1 kilowatt of item. So you are getting multiplier of 10x or maybe even 100x. So, and contactors are basically beefed up a relay system. They are far more powerful and designed to handle some big puppy. Basically, whenever you're dealing with big ass induction motors and all that, those are the very desirable things. So relay, contactors, but they do come with the penalty. They have a moving part, meaning it will wear down. If the spring power becomes weak, which again, after enough cycle, it will fatigue out. It's a consumable item. So if you look into railway system, relays are always designed to be a clip-on item because they're gonna wear down, meaning throw it away, put a new one in. It's a consumable. So it will wear down. And not to mention, it also consumes power because again, there is a giant electromagnet that had to stay on in order to keep it on. So that's a problem. And in sort of thermal system, we use bimetallic system. Now again, inherently it has a fatigue limit because again, it sounds cool that we are twisting a metal, but metals do not like to be twisted infinite times. Again, they have an upper limit, and not to mention they are very sloppy, meaning if you set your thermostat setting to like 40 degrees Celsius, you could get 41 degrees Celsius, 45 degrees Celsius, or maybe 38 degrees Celsius. It's not tight. Like from what we have right now in modern electronics, you like 1/10 of a degree Celsius is like, that's how accurate we are. Thermostat is like, so it's a very loose device. And not to mention, because you are contorting a metal, it's inherently not a very, what you call, long lasting thing. So either it becomes sloppy over time, or it's basically, it does work. And again, humanity is built on top of it, but they are like always, what you call, something left to be desired. Basically, we want something that is longer lasting, meaning it should not be a component that we just throw away. Like it should not be, oh, open the cabinet, throw away the relay. That should not be a thing. And then you also have to understand, they're hard to control, because what if you want to control, let's say, a signal, with a relay. For example, in an electric vehicle, when you have that DC main bus that is like 400 volt, 800 volt battery, you do not want it to be on. So generally, this contactor has to turn on. But here's the deal. How does microcontroller turn this on? So you have a 12 volt system that powers has a step down converter that powers a microcontroller. Microcontroller drives a MOSFET. MOSFET turns on the main 12 volt coil system, and then this puppy turns on. So you have extra steps. It's not done, go home. So inherently it creates a scenario where it's like, yeah, we have too much steps in order to take. So we want something that is easy to control. And again, not to mention, this also has a what we call back EMF. So if when you disconnect it, this tries to fry everything. You have to have another diode just to clamp that puppy. And we want solid state, because again, while it does look cool that, oh, metal is bending, like, ooh, yeah, it is inherently fatiguing it. So and again, spring will fatigue, the metal will fatigue, the contact will wear down. We want something that is solid state. So we are cool. We are cool with this. Humanity became basically crossed industrial revolution because of this. It's cool, awesome. But we need something better. Basically something that is longer lasting, easy to control, and solid state. So it should handle a vibration environment like there is no tomorrow. Behold the Triac. Now, Triac is a semiconductor switch. Now, if you know anything about any type of semiconductor switch, you will always know one thing. It's always designed as DC, meaning be it MOSFET, be it a transistor, they're always DC component. They either it's positive side, negative side. It's not AC, as in like it's not going to positive and negative, positive and negative. It does not deal with that. So, Triac is a specific device designed for AC. Now, what type of AC? It's fluid in that regard. Now, of course, it does have upper limit. It's not designed for like 10 kilohertz of AC wave. It's generally suitable enough. Basically, even if you buy something like this, it's suitable for using 50 hertz, 60 hertz, 400 hertz of aircraft systems. It can easily handle that. Now, of course, it has an upper limit. Don't go to kilohertz and hundreds of kilohertz. But like it's a flexible in that regard. So it just needs AC. Basically, go from zero, come back to zero, go to negative, come back to zero. Basically, that going back to zero part is crucial for its working. It must go to zero. So, and what about amplitude? Again, amplitude is also flexible. That's why you will see the rating going as low as 24 volt to 380 volt. It's like, who the heck has 24 volt AC? Many times you do want that. Heck, many soldering stations, they have a stable, basically transformer that steps it down. And then how do you control it? Well, you control it in AC domain. You don't go to DC domain, you control it in AC domain. That's a cost-effective way of doing it. So that's why it will come at like lower voltage also. So 24 volt to 380. So it takes a little amount of voltage and current. So it's not as efficient as it could be, but it does take a little bit, current and little bit of voltage to trigger those puppy up. And then you can control 100x the power, meaning if you're sending a signal of 1 watt, you can easily control something that is 100 or hundreds of watt. And again, I'm talking in one jump, it is doable. So it does allow you to have very awesome power scaling capacity, meaning now you can literally have like, hey, I want to control this, let's say, big water heater that is like, 5 kilowatt water heater, and I want to control it by Arduino. One step, done, go home. One step jump. You do not need to like, okay, we have this MOSFET that turns on this coil, and then we do that. Now, one step, go. So that's a desirable part. And you can do two things with it. First, on and off basically is just a switch. You turn it on or off. That's awesome. And you can do phase control. Now, phase control is almost like reducing the voltage that is going into it, meaning you can dim the bulb. You can be like, hey, the bulb should behave like it's running on 100 volt. Bulb should behave like it's running on 75 volt. You can do that. So not only it gives you on and off ability, but it also gives you phase control, which none of other device will do. So for example, if you have a bimetallic strip, you cannot say it like, hey, once the, let's say, water reaches to 40 degrees Celsius and let's say target is 50 degrees Celsius, you'll be like, hey, let's tone it down. There are sometimes people would like to do that. Let's tone it down. Or like if it's a room heating element, maybe you want a, falling curve. Basically, once you start it, it's a cold room, you want it to like go YOLO as high as possible. But then it's like, don't do on, off, on, off, on, off. Do calm down. It's like, that heating element that is 1 kilowatt, make it behave like 700 watts. Make it behave like 500 watts. You can do that. So not only on and off, phase control. That you cannot do with any coil-based system. I mean, like technically you can do PWM, but you will find those relays and contactors will wear out almost in hours. And again, you can easily find a spec sheet of any relay or contactor. The on-off cycle is not in hundreds of thousands. It's not that long-lasting device. And you can make it work without microcontroller. Let that sink in. While we may think Triac as a modern semiconductor device, it's kind of old and it does not need what you call microcontroller. You can have microcontroller. You can do advanced control loop with it, go YOLO on it, but it's not necessary. And that's the beauty of it. As in, you can design a very simple system, no microcontroller needed, or you can go YOLO. It's like, no, I'm going to have this 10 to 20 feedback loops to control it precisely. You have a lot of freedom. So this is how we got into what we call solid state relay. So what's the logic behind this puppy? Well, the logic behind this is somebody figured out latching transistor system. Basically, PNP making love to NPN. So these are two transistor. Now, here's the deal. If you know anything about switches, you know switch are naughty puppies. Meaning, on principle, you're like, I press the switch is on. That's not how it works in real life. Basically, if you have an oscilloscope, you can look into it. You turn the switch on, it's got so there is what we call debounce. The springs are like bouncing. So that creates a hassle. And that's a noisy signal. And you can easily understand why you do not want noisy things going into multi-kilowatt equipment. That's like, no. So what if you send a trigger signal? Cool. The NPN transistor starts to pull down. Cool. Awesome. But PNP is arranged in such a way that it creates a feedback loop that draws more power from NPN. Now it's like, ooh, that creates feedback loop into this. Now, so this becomes a system where it just latches. It's almost like how you have multimeter. Now you touch it a little bit, ting! So it's literally like it latches. There is no debounce. No matter how short the signal is, either the signal will work or it will not work. There will not be a scenario where you are like in that floating scenario, it's like none of that. Like signal goes in, either it's on or off. There is no hesitation. Now you must have seen a problem. If it's running on a feedback loop, how the hell you turn it off? Neat part, you don't. That's why it needs AC signal. It's not turning off, because to have a latching system and you want to turn it off, you have to cut off the VCC, basically the voltage supply. How do you turn off a voltage supply? Well, you don't. You wait for AC sign to go to 0. That's all you're waiting. Like you turn it on whenever you want to turn it on, and then you wait for it to go to 0, then it goes to 0 state, as in off. You turn it on, wait for it to go off, and then at 50 hertz, it will happen 100 times a second, basically. 100 times a second it will go to off, and in DC, DC I'm saying like 60, it will do 120 times off. So you are not turning it off, you are only control of when to turn it on. So let that be very clear. You turn it on, you have full control over the off is directly on the frequency of the AC mains, or it could be aircraft mains. That point in time is 400 hertz. So that is there. So current goes to 0 because voltage goes to 0. Tada, it turns off. Basically VCC is 0. Basically you cut electricity here, so it's there. Basically the moment VCC goes to 0, this signal is now ready for next pulse. Either you can send the pulse or you not send the pulse. That's up to you. Now, this is why we classify this puppy as leading edge AC control, meaning once the voltage starts to go up, you control it. As in like, do you let it pass or stop? That's the only thing you control. Basically, should it pass or not pass? So that's why you get leading edge control. Because once it's going down, you do not control it. Like you cannot turn it, let's say you turn it on here, you can't turn it off again. You have to wait for AC sine wave to turn it off. That's why you only have control over the on side of things. So leading edge. Now that is noisy, meaning specifically with basically when you are talking about capacitive load. So worst case scenarios, let's say the AC wave was here, 220 or 250 in some scenarios. 250, you turn it on. Capacitor acts like a dead shot, and imagine instead of going from 0 volt, it directly gets slammed into 250. It will create a bonkers amount of harmonics, and it will be brutal, might even destroy components. Now we're like, can't that happen when you press a switch? Yes, but here's the, whenever you do that with a switch, it's one pulse, right? Worst case scenario, turn the switch on, it's here. But here's the, when you are Triac controlling it, as in like partial control, partial as in like you do not want 100% power, you want 50%, it's happening every pulse. That's a completely different one pulse. Like who cares? Like that will destroy things. That will like kaput things. So generally, it's not recommended to do Triac dimming for capacitive load. Inductive, you can deal with it. That's why you will find inductive system where you have motor controller that is directly Triac based. It's just brute forcing Triac. It can be done. Not recommended, but it can be done. So this sort of partial control, what we call leading edge AC control, it can be done, it is done, it's not recommended, not anymore. Basically, we have crossed 1990s and we do not like this because again, it creates so much harmonic, it fries everything else around it. And now again, back in the old days, it was not an issue, but in modern sensitive electronic industry, it's like, yeah, it's noisy, it's too noisy, it's ugly. So do we have a solution? Yes. Solution is what we call 0 volt crossing. Basically, you do not do partial system, basically do what you call temporal on-off, basically on, off, on, off. That's how you do it. You do not chop the voltage, you do not reduce it, you PWM it. Basically, duty cycle, you control basically how many pulse I'm sending through you. Now, the resolution does go down because again, in a DC system, absolute DC, let's just say you have perfect DC element, you have on off whenever you want it. Here you have on off when AC mains wants it. It's like 100 times in a second if you are 50 hertz, 120 times if you are in a 60 hertz. So you do get that what you call master signal. In that you count like send this pulse, do not send this pulse, send this pulse, do not send this pulse. So this allows us to have smooth operation. And this again works very well with AC. And again, because of the design, you actually get better system than a switch also. Because again, under no circumstances, if you have a 0 volt crossing, you will ever turn on an appliance at here. Meaning if you have a heating element, it will slowly ramp up. It will not be like, boom, 250 volt, boom. So that will not happen. So 0 volt crossing became the what you call desirable system nowadays. However, it does come with a penalty that you do need a microcontroller. With Triac, you can control it dumb way. Like basically you must have seen this sort of heating element, soldering iron, quite cheap. You can buy it just for experimenting, and it has a basically potentiometer, some capacitor, some resistor, a diac, and a triac. That's it. So, and yes, it does control the power of this heating element, as in at full load it will go YOLO at 40 watts. At low load you can make it as low as, in this scenario, it's 19 watts. So you get like you have a throttle into it. So, and the circuit is super simple. You have the load, and then you have a potentiometer, that is your control knob, and then there is another resistor, and that other resistor feeds a capacitor. Now that capacitor is your tank. Now capacitor is connected to diac. Now what the hell is diac? Diac is a diode which conducts in both ways. Now like, wait a minute. What's the point of a diac if it conducts in both ways? You know about diode. Diode conducts in one way. That's the whole point of a diode. What is the point of a diac? Well, diac is almost like a voltage gate, as in it will not pass, let's just say 2 volt. If you are below 2 volt, it will not pass. If it's above 2 volt, it will pass. Think of it in that way. It's like it will allow AC sign to pass as long as it's not a zero. Depending on the design, it could be 2 volt, 3 volt, whatever have you. It will only pass that. So that gives the benefit that it will only send a signal when it can actually turn on the triac. Triac has some voltage, meaning you can't send signal of like 0.5 volt and expect it to turn on. That's not recommended. So that's why I said like this latching system does require the signal has to be strong enough, only then it turns on. So that diac is acting like a buffer, where it's like not enough pressure, not enough check valve, not enough pressure, not enough pressure, go. And how much energy goes, that directly controlled by your capacitor. If your resistor is set to the lowest setting, capacitor charges up quickly, full signal goes. Capacitor, you increase the resistance, capacitor takes its sweet time to charge, only a small pulse goes through. So that's how we control it. It's quite simple, ingenious even, for how little of component you need and how much power you can control. And then all you have to do is basically change the driving circuit from diac to optical coupling, and then you can have microcontroller system, which again that will be needed if you want to do zero gate crossing. So this is the logic behind it. Surprisingly clever use of it, but it does consume bit of power, meaning if you are really turning on and off some heavy loads, like let's say oven or things of this nature, you would require to add some cooling for your thyristors. Triac. So what are the use of this puppy? Well, it's allowed us to replace a lot of mechanical systems that are driven by basically AC main system, relays, switches, lot of things. And again, it is used for what you call motors also, especially with zero drive circuit, because again, you can turn on motor precisely as you want to. And again, if you're not doing partial control, it is really good. And if all you want is on and off, it is really good. So if you want to use Triac as on-off device, basically either it's on, either it's off, shut up, take money. If you want to do even better on and off, do zero crossing. It will never send a full pulse. Super awesome. If you want to do control, okay, you can do for small loads, it does not matter too much. You can do that sort of naughty, what you call pulse control. Chopping, so to say. But again, if you want control, like let's just say you're dealing with something serious, it's a heavy load, but you do want to control it, again, have 0 volt crossing circuit, and tada, you get to control it. So you have a lot of flexibility, lot of latitude to use it. And it's really amazing for resistive load. Again, inductive also and capacitive also, if you only want to turn it off. Nobody would recommend you to use this on capacitive system when you're doing partial control. That's pushing it too much. Inductive, you can push it, but on and off, you can do all three. On and off with zero crossing, you can do it better than any other system. But capacitive, try to stay away from it. Inductive, it can chug through it. Resistive, it loves it. It's like, I'm good. So like soldering irons, soldering and clothes iron and dryer, toaster, kettles, basically anything that has giant heating element, it loves that. And zero crossing allows you to remove the harmonics penalty, because again, that's why modern dimmers cannot have this sort of system. Dumber, like, this sort of system, because you could be switching 100 watt item to 500 watt item. At that point in time, harmonics will start to affect other things. So there's like, hey, let's handle it very effectively. And not to mention, people figured it out, it's not that hard to do zero crossing, simply because you can have an optocoupler like MOC3041, which again, many this. It's just that it has its own zero crossing circuit, meaning the control signal that you are sending from other low voltage side, if you turn it on and the voltage is not at zero, let's say voltage at worst case scenario 250 volt, it will not do anything. It's like, bro, I'm gonna wait. Only when it goes to zero, then it turns on. So this system, even if you're not doing anything advanced, it still saves a pulse issue. And with advanced system, this acts like a filter where it's like, no, 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 not the right time to turn on, right time to turn on, wrong time to turn on. It does all of that. So this is a really clever way of doing it. And again, it is not perfect, absolutely perfect, because it does let a 20 volt slip through, simply because the zero crossing circuit, as in the detector that is detecting when that 0 volt is happening, it's powered by the same signal. So it does not have an independent signal where it's receiving it. So it does have that tiny window where it's like not absolutely perfect. 99% perfect, but not absolutely perfect. If you want absolutely perfect zero crossing circuit, it ideally has to be independent of it, meaning it should not be powered by the same device. This we try to do cheap and best. It works, it's really good, but does have a little bit of a wiggle, so to say. So really amazing device, got us so far. And again, many things have been replaced because of this puppy. Many things, mechanical things. Throw it away to like, hey, put it once in a while, once in a blue moon, it will be fired. So what can we expect in the future? Well, in future, Triac is more efficient than coil. We know this. We tested it, known this, done. And again, compared to relay and contactors, it's not even a discussion. However, we have an even better system now, meaning Triacs are two, basically structurally, it's a two PNP and NPN junction married to each other. But what if you married two MOSFETs? Because again, you know MOSFET does not care how the current goes in which direction, but MOSFETs have a diode that blocks in one way. So if you had only one MOSFET and turning it on and off, it can handle the voltage. You can buy a high voltage MOSFET. It can handle the current. You can buy high current MOSFET. It will only allow 50% power. Basically, it can control whether it's 50% or 100%. It will not be able to 100% because one of the wave will go through, either the positive wave or negative, it will go through. So you have to put two of these puppies. So the body diode blocks in both ways. Then you get to off or on it. So, and why would you want to, instead of buying one item, as you can see, one, what the hell I removed from it? Okay. So instead of having one Triac, you have to have two MOSFET, and MOSFETs are expensive. So why do that? Well, MOSFETs have very low on resistance, meaning how much heat sink you need for your Triac goes away. Like many people buy this sort of cheap, what you call soldering iron, and it does not last very long. The Triac burns out. Why? Triac, again, many cheap designs do not actually solder it to the PCB, and there is no heat sink, it burns out. MOSFET can handle much more with much less self-heating. So that's the first point. Not only you are saving power, but you are also making your life easier. For example, if this device is in your soldering iron station, you do not need active fan to cool it. But if you have Triac-based system in older design, you need an active fan to cool it or big ass heat sink. So there is a genuine reason to go to a MOSFET. And it basically, you have to have a complex driver. It cannot run on dumb system. So you have to have a complex system. Now, thankfully, because of the modern development in IC technology, complex MOSFET simply means buy a 10-cent MOSFET driver specifically built for this. Or you can do this with a normal Raspberry Pi or Arduino if you want to, ESP32 if you want to. But it can be done by a dedicated device, let that be very clear. It's a doable, you can do that. And this also allows not only on and off, it also allows trailing edge chopping, meaning people would love this idea that, hey, not only I'm controlling on and off, but I'm also reducing the actual impulse, actual oomph that is going into the device. But generally, you do not want to do that because it creates very naughty harmonics. What if? And 0 volt crossing, while it is really good, it's not what you call fine enough resolution because you are at the mercy of the AC grid frequency, which is 50 Hertz, not that refined. And sometimes you may not want that. You may not want that. So in that time, trailing edge chopping is the best way. Why? Because again, let's assume you want to dim a LED light. If you do not reduce the voltage, the light will flicker. If you're waiting for one pulse, another pulse, it will flicker. You will see that. Our eyes can see 120 Hertz signal. So it will flicker like mad. So trailing edge chopping allows you to basically let it on, and then turn it off. Meaning it never gives that shock impulse of 220 directly on. No, 0 to 35, 0 to 35. Like if you set it to low, it goes from 0 to 35, 0 to 35, 0 to 35. It's not going from 35 to 35 to 30 and then 0. It's offsetting in from different direction. The benefit is harmonics is much less, not 0, but much less. And again, if you buy in modern times LED dimmers, That's what they are doing. Incandescent bulb does not care either it's leading or falling edge, but trailing edge does allow you to work with, even with capacitor based droppers that we have for LED bulbs. Actually managed to work. Like, again, it's not desirable to have them, but you can. So this is the future where we get almost all the benefits of zero voltage crossing and chopping of the signal, where you do not have that bad harmonics. Now, it's a midway compromise, but again, you can do that. You have that option. So not only your heating element will go on off, which again, if you are doing very low power, it may not be required, desirable, because again, it's literally pulsing the elements on, off, on. It's pulsing the element. You may not want that. You may want the element, heating element, to cool down to lower temperature and stay at that temperature. Like if it was full 500 degrees Celsius at full signal, you want it to be like, hey, go to 300, stay at 300. Do not go like thermal shock. Thermal shock, it will reduce its lifespan. So this can do that. It's like, hey, I got this. You are at lower temperature, stay at lower temperature. I'm going to reduce your voltage until your temperature stabilizes at that. So from heating element point of view, it's now getting 30 volt AC. So it's like, hey, I can maintain the temperature. I will not go off. So the thermal shock will be minimized. And yes, does it have an effect? Not on day 1, but on day 10,000 it has. So it's a very interesting progress that we went from a simple but naughty device to complex but elegant device. So this was my presentation on this Triac technology, aka AC mains semiconductor. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.